The next reaction we are going to discuss is oxidation of alcohols to carbonyl compounds and carboxylic acids. If you recall, in the previous section, we have mentioned that carbonyl compounds including aldehydes and ketones, as well as carboxylic acids, can be reduced to alcohols under various conditions. So this reaction is essentially just the reverse of that reaction. So if you want to oxidize primary alcohols, we can oxidize them to either aldehydes or carboxylic acids using aqueous potassium dichromate 6 and aqueous sulfuric acid, or acidified potassium dichromate 6 for short. But there is a need to change the condition depending on whether you want to obtain the aldehyde or the carboxylic acid. If you want to obtain the aldehyde, you will heat the primary alcohol with aqueous potassium dichromate 6 and aqueous sulfuric acid with immediate distillation. Whereas if you want to obtain the carboxylic acid, you will heat the primary alcohol with aqueous potassium dichromate 6 and aqueous sulfuric acid under reflux. If you want to just obtain the carboxylic acid, you can alternatively use aqueous potassium manganate 7 and aqueous sulfuric acid. Take note that because aqueous potassium manganate 7 and aqueous sulfuric acid together is a stronger oxidizing agent than acidified potassium dichromate 6, we are unable to obtain the aldehyde if we are using acidified potassium manganate 7. So this is the equation for the reaction. The O represents an oxidation reaction, and this is the convention by which we represent organic reactions involving oxidation. Next, you'll see this diagram in your notes, and this diagram shows the setup to obtain the aldehyde by oxidation of the primary alcohol using acidified potassium dichromate 6. So before we talk about this setup, a bit of background. So because of the nature of the intermolecular forces between alcohol molecules being intermolecular hydrogen bonding, but aldehydes, they are unable to engage in intermolecular hydrogen bonding. So the strongest type of intermolecular forces between aldehyde molecules is PD-PD interactions, or permanent dipole interactions, which results in aldehydes having lower boiling point than alcohol. So this is the alcohol in a flask with heating, and you're going to add the acidified potassium dichromate 6 dropwise while heating. So the moment this acidified potassium dichromate 6 touches the alcohol, it will oxidize the alcohol to the aldehyde. But since the aldehyde's boiling point is lower than that of the alcohol, as the aldehyde is formed, it immediately vaporizes. So the vapor is going to rise to the top, where it comes into contact with a condenser. And the condenser is supplied with water. It provides a cool surface for the hot aldehyde vapor to condense and drip down as distillate. Next, we are going to look at secondary alcohols. For secondary alcohols, you can use either acidified potassium dichromate 6 or acidified potassium manganate 7 to oxidize them to ketones. Ketones are unable to be oxidized further. Finally, for tertiary alcohols and phenols, phenols are compounds with OH groups bonded directly to the benzene ring. Tertiary alcohols and phenols do not possess hydrogen atoms on the carbon atoms which bear the hydroxyl group, and as such, they are resistant to oxidation by both acidified potassium dichromate 6 or acidified potassium manganate 7. Okay, now let's look at exercise 6 to predict the products as well as to give their structural formula of the products formed when the given alcohols are being oxidized under the conditions given. So the first one is a primary alcohol because you see a CH2OH group here, and we are oxidizing using KMnO4 with H2SO4. So under such conditions, the primary alcohol will be directly oxidized to a carboxylic acid. So the CH2OH group becomes a COOH group in the product. Secondly, we have this cyclic alcohol with an alcohol bonded to a 5-membered ring. this is a secondary alcohol because there is one CH bond on this carbon that is not reflected in the skeletal structure. When we oxidize it using K2Cr2O7 in the presence of sulfuric acid, the OH group is converted to a ketone. So you will oxidize it to cyclopentanone. Finally, this is a tertiary alcohol. There's 1, 2, 3 alkyl groups attached to the carbon which bears the OH group, so it will not be oxidized by acidified KMNO4. Finally, this oxidation reaction of alcohols can be used to distinguish between the various classes of alcohols. So we will warm the alcohol with a mixture of aqueous K2Cr2O7 with dilute H2SO4, and we will look for a color change from orange to green. So if the acidified K2Cr2O7 changes from orange to green, then we will conclude that the alcohol is either primary or secondary. But if the acidified K2Cr2O7 remains orange, we conclude that the alcohol is tertiary. Finally, please take note that this reaction cannot be used to distinguish between primary and secondary alcohols. To do so, we will need to oxidize the alcohol first and then to test for ketones using reactions that we will learn more about in the next topic on carbonyl compounds.